Hello and welcome to my combo bedroom. We are not outside in the classroom at the moment for two reasons. The smaller one being that it's dark and we'd have to deal with all of our candles, which that's not the main reason because you know I enjoy playing with candles. The main reason is that some more huge chaos occurred on our set recently on purpose because it fits in with the next episode. I mean, it was not actually, it was semi known that it might happen. But the exact timing did quite catch me by surprise, too. So, some things are a mix of anticipating a potential surprise, but still letting part of that surprise hit you. Now, there's a particular topic that makes sense for me to cover as a channel that likes math that at some point will be good to dive into that relates to a particular type of chaos. The relationship is, mostly a mild connection, but in any case, the chaos that occurred is something that did also happen kind of similarly in grade -1. Now, if anyone wants to leave a guess, they can feel free, and perhaps at later in this stream, we will take a little visit there. That would probably be right at the end of the stream if we do that, because it would be a mild spoiler of some chaos that occurs in the next episode, so people could choose to opt in or out of that field trip. For now, though, we are playing around with some wacky graphs, and let me just make sure that it's synced up correctly. I just changed something on my end. Let me make sure that I can see it change on the stream, because of course there's a mild delay to get my info over to you folks. So let me see if it actually changed, and it did. So we are good to go. Now, today, since I'm indoors right now, I don't want to either bother my family to a huge degree or have too much background noise. So what we're going to do is put on some of my music I've made in the background, some random beats that I created that I use in soundtracks and such. And right now I'm going to try and run them through the computer and turn off the fan I had going. And let me know, it's going to be hard for me to tell whether I have them at a decent volume. So let me know if you think that the beats are impossible to hear, meaning I should turn them up, or if they are drowning out my voice in any way. So, we'll throw on one of my beats while we begin discussing how we are going to look at some crazy graphs. And, real quick, also definitely let me know if there's any weird delay due to the fact that I'm playing the beat through my computer and some of the audio is coming through the bit recording my voice. So, because of that, let me know if there's, for some reason, they sound like there's two beats going at once. Now, what we're going to fiddle around with today while we chat is a classic topic here. We love fiddling around with making weird shapes with graphs maybe every 10th stream or so. It's a hobby of mine that I found you guys find entertaining as well. And today I found some new ones, so I was like, before I start messing around with all the variables, let's turn it into a live stream. I got a little time, and we'll fiddle around with the variables together. Now, what I began with was the background of what I put in the thumbnail, and that was putting something like, say, starting with y being less than or equal to a trigonometric function, in this case a sine of x, over divided by a modular function. Now we do a lot of modular arithmetic of on the channel where things wrap around. The way they phrase things on this online calculator means here we're taking y in mod x. Normally it would be written a little different if you were just doing number theory, but this is how the, my favorite free online graphing calculator works. So if I were to just do that, it already looks pretty crazy. In fact, at this angle, I almost see like a spider-like shape, like a little abdomen and some legs. Now, when we zoom in, we see more, and when we go far enough out, maybe they don't say it on this graph, but sometimes they say this graph is too detailed for me to tell you everything about it. If you zoom in, you keep getting more detail. We're going down an infinite hallway, essentially. And so at certain points, they're unable to get the detail, and we slide out to scales where we can see the detail in a particular section. Now, these points that are thick lines are exact equals, and the shaded parts are when that part of the equation is greater than that part. We could flip the inequality and it would look like that. And what I had started with, even though I almost like this more, I might go back to this, was putting a sign on the Y as well. Now, this zoomed in looks kind of like that spidery thing, but zoomed out sort of repeats. We get things that, funny enough, these lines, they start out glitching a lot, and then they glitch sort of less and less. And at some point, they look pretty straight. The more you go down certain directions, you typically are looking like you're getting straighter, but there is one diagonal that does a weird thing. Many diagonals as we get closer. Now, zoomed far enough out, they're having some trouble right here. Oh, this is this thing. This is this glitch that they talk about. I don't know if this is the first time that I've gotten this glitch, or okay, there's a nickname for this. I was on the Desmos subreddit, and because I was like, maybe like they would like these graphs. I haven't posted on Reddit really, even though there is a combo class one. And one of these days, one of our streams I want to do is going through the top posts on the math memes subreddit, because there were some funny ones on there. But I read in the Desmos subreddit that they nicknamed this shape Bernard. I think this is Bernard. And I don't know if this is the first time I've met him myself through an equation, or if this is the first time I've met him since I knew his name and was introduced to him. And, okay, I gotta pull this up. Now, whenever I change the view on my computer, I usually go all the way to myself because I'm such a non-tech wizard that I'll probably, accidentally show all of my photos or all of my notes for my next episode or, something. I don't really, I'll eventually mess up and accidentally show everything on my computer probably because I'm such a non-tech wizard. But usually I will pull the camera to myself when I switch pages just in case. Now, let's see. I'm going to go to the Desmos subreddit and see if I can find... Part of the reason why I feel weird is when I Google stuff sometimes, they're like, do you look for results near this area code and this location? And to any stalkers, I will say that when that came up, that may or may not have been accurate. There have been ones that have flashed up before that were inaccurate when they were guessing my location. So no stalkers trying to get any data from that. But I still don't want them flashing up their guesses of what zip code I'm in, and I can't get all the main browsers to turn that off. Once again, I'm not really a tech wizard compared to other skills. Now, I swear on this Desmos subreddit, they talk about this shape. They call him Bernard. Let me see if that's really the case. No, see, this is what I'm talking about. No, I don't want to sign into Google. Stop trying to get me to do personal information. I need a separate computer to stream on. Right now, I do not have a lot of money, so we do everything on one computer and one phone and occasionally one DSLR camera. So we're low budget right now still. There's a Patreon to anyone who wants to help. And there's also YouTube memberships on this channel, even though I still need to link those to the videos that I put on Patreon. And I still need to finish editing all of this really long bonus video that I have for Patreon coming, even though I've been promising it for a while. It will actually be coming soon. Now, here they're just chatting about their things they found in Desmos. That you can do a lot of stuff if you like want to use Desmos as like a computer program in a way. You can go kind of crazy on it and make animated like things that move. I'm not trying to make the most complex thing I can in Desmos though. I'm trying to find the simplest equation or the biggest ratio of difference multiplicatively between the equation's simplicity and how crazy of a landscape I can create from it. So, as an example of that, like if I just take the circle equation because we're a few days after Pi Day. No, wait, don't move that, move me. If I just take this, Bernard, we'll come back to you in 1 second. If I just take the circle equation and normally I could say like x squared plus y squared. I'm putting them in quotes for a reason. You'll see. Plus y squared, I mean in parentheses. Equals r squared, but right now I could just call it r and assume that the square root of that is related to the radius. So if I just have that on there, I can make a circle. It's really small because we're really zoomed in. Oh no, I hope I didn't lose Bernard. Okay, we'll re-find him. But now, right there, that's a circle equation. However, okay, I'll come back to the big scale to make sure we don't lose that shape that I want to tell you about. But if I throw sine on both of these, I noticed one day, we get a really crazy thing. Now, if I set r to 0 and zoom in, oh, and let's do it as an inequality. So normally it would either be a filled in circle or everything but the circle. We get this at 0. It starts mutating as we go to 1. And then they merge at 1 right there, and then they start splitting. And this is just adding sine to the circle equation. That was probably the first one I found that got me hooked on doing some of my streams and as just as a hobby, messing with graphs like this. So my goal is to find the simplest equations that still create vastly cool landscapes, sometimes combining a few equations at once. We'll remove the circle one for now so that there's room for me. I was probably blocking a lot of the coolest parts of it. Trust me, that one's cool. We've done it in a lot of previous streams, though. So, anyway, moving to what we found today. First of all, this is one of the ones I fiddled with. And then first I was like, let's make this more symmetrical by switching the x's for y's. And so here I switched the x's for y's. Y turned to x, x turned to y, and here we flip the two. And now, these are different colors, but we could make them the same color for now. Although, okay, I lost that guy. Well, you saw that shape earlier in the stream. Well, they talk about this thing called Bernard in here, I swear. It's like this glitch that Desmos has, and maybe they don't remove him because he's become like a meme or something. Look, wasn't that what we found earlier? Didn't we see a version of that? So, yeah, this is some glitch that Desmos has that happens frequently enough that it's gotten nicknamed Bernard. So that's fun. Maybe we'll meet him again in the future. Anyways, we can quit that and go back to our calculator and maybe come back to that later if we want. So here things are in a way more symmetrical. They still are trippy due to where I put the signs and the mods. And now if we really wanted to flip everything, we could flip that too. That makes it symmetrical in a whole different way. But for now, we'll keep these going the same way. Now, what I went to from there Let me first see what our chat's saying. Hello, everyone. And someone says put old in front and I won't get bad new Reddit. Normally I would read all... Okay, I'll just read the quote. This is... Sorry, kids, I'm gonna read the quote. They say new Reddit bullshit. And, yeah, I don't know anything about old versus new Reddit. I know that I don't use much social media, and that one I find half decent. So I go on there occasionally, but I'm not a big social media guy anyway. And we have some other comments about health and stuff. And yes, I'm doing healthy today. I have been experimenting with different medicines from doctors related to mental health because, like many humans, I deal with mental health issues. And I do need to take different medicines that I'm still exploring because I have a complex brain. But in general, my health has been improving by a long shot. There are times in grade -2 where I was not the healthiest, and we'll discuss some of those things in the grade -2 finale. Others we may need to wait a little longer to discuss. For now, we will leave it at that. Now, as far as our graphs go, moving from there, I figured we're pretty close to Pi Day, and because of that, what we should do is a few polar coordinates, which relate to circular things. Polar coordinates are another way we could plug in equations. These ones we could use r's for, so let me shrink myself to show that one. Here we have r being less than or equal to a bunch of cosines over a number and some of these thetas. It's a Greek letter, and we also need to set a range for how far they're going to look, because it's going to be a spirally sort of thing. Like, if I only put r being less than or equal to a particular amount of thetas, well, let's even just say theta. Here we get this spiral, and I could just say it's equal to make it extra clean of a spiral, and if I wanted, I could make this begin at -12 pi, and then we would have sort of some symmetry. Or I could let it go one direction from 0 and go to about 100 or 1000. For now, we'll go with their default of 12 pi and adjust that when we want. Now, here, if I were to throw some sines or cosines, this time we'll try sine, although it's not much different than cosines. Sine of theta, that's tiny, gives us a little circle. And let's go back to inequalities as well. Now here, if I go for another sine in the mix, sine of theta, then what we're going to need to do is just see, okay, that didn't change much, but what if I multiply this by one of those simpler spirals? Like when we saw that I was just doing theta, it was going... So what if I multiplied some amount of spiralification, if that's a term, to one of these? Well, beginning with that smaller one, if I spiralify this, I do get something. And as usual, I could have increased the range, but then it's harder to find a scale where it doesn't look like all the lines are just covering each other. They can't make the lines infinitely thin, so if you're at some scales on some equations, they're going to touch. Now, when I threw another sine or cosine like thing in front of here, it's not working as well with this one because I'm just at 1 theta. Let's try and bump up the amount of thetas on this interior one. Now I had 7 on that interesting shape that was there earlier. And let's see, what if we just make a times theta, and we'll pass by 7 at some point. Now, if I bump A up a little bit, sometimes it's really chaotic, and its chaoticness depends to a degree on what my range is. Because if I made my range smaller, it's looking at, you know, we don't see too much overlapping. We can kind of tell it has this spirally shape it's doing. But if I set this really big, it's just going to look like it's blotting everything out because of the lines. Now, going forward a little bit, if we take this and go to certain multiples, like if I go to the number just 2, we notice, okay, these spirals are more contained. They're not overlapping each other so much that they're going to crush the whole screen, even if I bumped it up a lot. Only crush part of the screen. So what about 3? Like, is there a coincidence between, I said 2, and there's kind of 2 leaves to this flower-like thing? Well, in fact, if I go to 3, I do get 3 petals on my sort of flower. Now, if I go higher, up to 4, we get 4 petals, and etc. And I noticed that when I bumped all the way up to 7 petals, we got this to begin. And for some reason, my cosines were looking extra crazy there. These are sines when I'm doing that. And it would be the same thing as if I said 7 instead of A, because A is equal to 7 there. I may be blocking where it says A is equal to 7. Here, when I did them as cosines instead of sines, for some reason, this was extra crazy. Sines and cosines usually did quite similar things when we've played this game. Now, let's try and see what happens first when we just bump up what amount we have right here. So we're turning this one to A as well. I'm going to, let's see, either shrink or move myself so that we can see all this. Well, you know, I'm having a lot more fun with these ones than with the original backgrounds. So I'm just going to delete the backgrounds for now, and we can always come back to dividing by modular stuff if we'd like. Now we got enough room to see where we're at. So if I were to go all the way down to A equals 0, it almost looks like that first really simple one. R is less than or equal to theta. Now if I go up a bit, we see it mutate into strange shapes that at certain points seem to align, and at other points seem like they're just going chaotically. Now, let's see what happens when I up the range a little bit. Let's put the range, it was at 12 pi, which is going to be somewhere around 40. A little under 40, I would guess 12 pi is. So let's say our range is going to 100. Now, here we will zoom out a little more, but we can see this again where at certain times it looks kind of fixed, like they're lining up in correct-ish feeling places. They're not overlapping with their neighbors too much. Now as we zoom forward, we can see that there are spots where they do totally overlap their neighbors, and if I bump this up higher, they would wipe everything out. And there are other points, including ones that aren't integers, that aren't whole numbers, that do weird things. Here we have 0.5, and it's kind of like one we've seen before, but it's skewing a particular direction. You can almost optical illusion yourself to see this as a cone going inward or outward. What happens with the other 0.5s? Well, 1.5 looks very 3-like. 2.5 looks very 5-like. So we can see that the fractions sort of get to line up when they're a simple fraction of a number. But here, if I go to, these are in tenths due to the base 10 system, tenths end up being a pretty chaotic fraction compared to something like halves. Here we have 3 itself, which actually does 6 here. So that's interesting. That's why 5 was, or part of why 5 was so crazy. Because when we had 5 at a lower scale, at 12 pi, it looked like it was doing this wacky expanding thing, but really it was kind of trying to be 10. So for some reason, sine is just so much more interesting than cosine there. Now we're gonna try tangent, because that's another classic one of these trig functions, but tangent sometimes goes crazy. Warning, tangent sometimes just flies off the map. The way we were blotting everything out, tangent likes to do that more frequently. So let's try though. Let's replace them with tangents one at a time. That's if that one's a tangent. It just kind of went sideways. Here's if this one's a tangent. Now it's doing some interesting things. It's half the time doing those flower petals and half the time doing these like flower little sticks that look like what come out of my guava tree sometimes. Now what if we tan them both? So that'll be tricky. Whoa. Now that's one of the least cool, but it's still fun to zoom in and out of. There are other trig functions, and another that has turned out to be quite crazy can be the cosecant. And what we're going to do is go back to this being either both cosine or being both sine, or first let's just try a mix. What happens when one's sine and one's cosine? Oh, that's pretty cool. We get things spiraling at different rates. We can even animate these, but sometimes they make them go way too quick. So let's see if we can get a speed that's actually viewable. Yeah, that is really cool. Polar coordinates are a whole wild world of their own. And we did a pre-Pi Day stream, but I didn't get to drop anything on Pi Day. I ended up quite busy that day. So we'll consider this our post-Pi Day stream, because polar coordinates do involve pi-like concepts. Pi is essentially just related to circular motion and circular things in any dimension. Now, and we can even see it there that the default is in terms of pi of what range they ask for theta to be. Now, what happens the other way? What happens when this one's sine and that one's cosine? We get a kind of similar thing. Maybe not quite as cool, but still pretty neat. Rotating at different speeds that are in enough of a ratio to each other or have enough common factors that they do line up at, oh, whoa, so that's cool. It lined up at 3 right there. It's going to line up at 2 right there. It's lining up at different numbers. So look, 1. It lined up at 1. It's going to maybe go back to 2. So yeah. There it lined up at what? 0, I guess, looks like here. So, and then let's see if we can get it to line up at 2 again. There we go. Now it's going to line up at 3 next. There we go. That's pretty cool. It passes through all those different phases. Now, what happens when we switch one of these with a cosecant instead? This gets to be whole other worlds of weirdness. This has those tangent-like fronds, but kind of flowery things, but they're kind of dolphin tail-like. And we can get it to spin as well. And now we're going to see if that was cosine right there instead. Pretty similar. But whoa, that one's a little more chaotic. Now we're going to see if the cosecant was here. And whoa, that's if they're both cosecants. I'm kind of scared to press play. First, we'll put this one into a cosine. Whoa, that's interesting. It's a similar shape in a way to the last one, but a little less scary looking to press play on this one. Well, yeah. Whoa, that was cool when they hit it. So sometimes they line up in these particular ways, and it is related to the number that the A is on. Now, right now, A is actually going back and forth from positive to negative right here. But when it's negative, it does similar things to positive. At least in terms of when they line up. Some equations even do identical things for the negatives. Some are just similar in terms of what number it causes them to line up on. So this one's pretty cool. Now, what will happen when we make this a sine instead of a cosine and try the same? Pretty similar. Yep, and we get into like a 2 like ones, and there's a 1 like one, and there's the one that's a 0 like one. 1 like one, we're gonna go to a 2 like one sometime, 2. We're gonna get to a 3 before too long, 3. All right. And this looks like a 6, but that's not what I meant by a 6, really. What I meant by 3 is when we get these huge gaps, it like really lines up at certain points. So now we are going to try when they're both cosecant. Whoa, that's interesting. Look at those bumps. We weren't zoomed in this far before, I guess, because now I can see something different. Now, if I expand the scale of this, are the bumps going to grow? Yeah. Well, now that's a little too much. So how about just 120 not times pi? Yeah, so now we got some medium-sized bumps there. And let's see what happens. Oh no, that's way too crazy. So some of them I have to pause right away because they just flicker almost instantaneously, like at the speed the computer program can, between these absurd different states. Now, somebody asked, how did I get the knowledge? A lot of it was from personal experimentations, just because I have fun writing notes and doing random things like this and thinking about things like numbers and trying to connect different concepts. A lot of the other knowledge came from reading. I read a lot of books and articles, so those are super important to study from, in my opinion. A bit came from school, but personally, people learn different ways. So I have learned better through those first 2 sources I mentioned. All right, and somebody's joking that it breaks the PC, and we kind of have crashed it before in different ways. Not completely crashed it that it made the whole stream crash, but there are times where I had to reload the Desmos page because it started acting weird. Now, and if anyone does like this stream and doesn't know, there's probably the 4th or 5th wacky graph stream that I've done where I sort of just try and find new ones and am marveled by their coolness. So if you scroll back on the live tab, because the live streams are saved, kind of like videos, you can find anyone with like graphs in the title probably relates to this or might relate to the other concept called graph theory, which is actually really different than this, but you could probably tell from the thumbnail. So this one we're going to scroll through to find cool things, but we're not going to do the animation. So 4 does make 4 nodes that have those waves. We can kind of guess what will happen at 5. Let's see if 4.5 tries to go for 9 of them, because sometimes the halves were like doubling it, as if they were trying to get to the integer that they were a factor of. Now, I mean, there's many integers. 2.5 we don't even call a factor because it's fractional, but if we considered fractional things to be a factor, then you could say this is, you know, a factor of many things. So I guess it goes for the, quote, factor of its smallest whole number friend. And 2.5 does make 5, so I feel like 4.5 might make 9. Yeah, that's 9, right? Let's see. Let's start from here. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, we got 9 right there. So that's pretty neat. The problem is that we can't do thirds. You know why we can't do thirds? Because we're stuck in this terrible base 10 system. We can do fifths, but not thirds. Thirds would be the next one to logically try and show how it triples the amount of things, but won't do that because going to 0.3, even if I try and up the precision to 0.33, will not be enough. Can I set this as a fraction? Can I set this as 4 1/3, which we'll just try and put it as a mixed number, I guess. So we'll put that as 13 thirds. Yes, we can do it. Okay, that's awesome. This is why this is my favorite graphing calculator. They usually can do the weird things I ask. Now, so we actually can do thirds on this calculator, but many calculators don't do that because they work in terms of decimals, or many calculation systems at least. And so fifths are given priority over thirds. This will probably return within the rest of grade -2 because I did a threeven episode in grade -1 about how I think the word threeven should be in the dictionary, and about how someday when the time is right, I will start a petition, and the petition will probably be in grade -3 to fully line up with our threevens and our correct timing. But I still think that I need to make another episode explaining even more cool facts about threevens related to different bases, related to all sorts of stuff. That there will probably be another threeven related episode in grade -2, which we are 3/4 of the way through, meaning that there will be 9 more main episodes on my main combo class channel. Make sure you caught the last one about modular exponentiation. That's linked in the description if you haven't. And out of the 9 more, the finale is typically some sort of documentary. The second last one is some strange version of a final exam, perhaps, but that's what we did grade -1. You never know what my strange version of a final exam might be this time. You know, you only have one example in your sample size. And that really only leaves 7 more full episodes in what I'm going to call grade -2. Before too long, my life will have some shifts as well. I'll be taking a trip in April, and then I will be possibly moving not too long after that. However, don't worry, the combo class is my priority, and when I'm looking at all these things like planning trips and possibly moving, my priority is to make sure that it maximizes my ability to do combo class even better in the future. Now, some other comments note that yes, it can do fractions, and it's hard to read this chat like this. It's like, I guess I need to slide this over. I just don't want the chat to be like blocking what the viewers can see. I need a second computer, definitely. I know legit streamers have like one computer that it's being run on and a different computer that they're like clicking some things on, but I only have one computer at the moment. So somebody says, yes, study other bases. And if you like other bases, go to the combo class channel because there are many episodes about other bases, many of which are the most popular ones on there. And we've done how to count negative bases, fractional bases, irrational bases, etc. And there will be more coming. We're going to do mixed radix bases, either late this grade or early next grade. Mixed radix bases include ones where the spots are not just powers of a singular number, and we're actually more used to them than we realize from clocks, because clocks are basically a mixed radix base, where the first part goes in either 12 or 24, and the other parts go in 60s, and then it's all written in base 10. So there's this whole mishmash. But in general, mixed radix bases include mathematical ones as well, such as the factorial base, the primorial base, and so on. And that episode may go into all of that, or it may focus on the idea of what are the possibilities, impossibilities, and limitations of if we were to make bases based around prime numbers. Now, which actually somebody asked right here, or any prime number. And yes, if you're just doing a standard numeral base where each one is the power of the number, you can make a base out of any whole number larger than 1 and follow all the same rules. If you switch to fractions and stuff, most of the rules hold, but you got to be careful when you're like, figuring out the details of those. I have made episodes about them though, and there could, but I will repeat again that the ideal base for humans would be a highly composite number, and that 2 is a bit small, 12 is a little bigger than we need, honestly, because how often is it that, like, you're talking about a quantity larger than 36, you'll see why I'm saying this in a second, larger than 36, how often do we talk about that and we're so annoyed that it's going to take us 3 digits? Or that we're talking about a quantity more than 216 and we'd be really annoyed that it would take us 4 digits. The reason I say that is because the highly composite number between 2 and 12 is 6. I think there are more highly composite numbers on the way from 2, but that's because they're so small that they break the record pretty easy. Like 4 should be highly composite, but we don't want to count in base 4. That's similar to base 2. That's good for computers. Now, that makes base 6 the ideal base, and that is far from the only reason why base 6 would be the ideal base for humans, but it is the simplest version of, or the simplest pitch out of many. And yes, there will be a time where I make a petition to get Threeven in the dictionary. And if anyone, don't make your own petition yet, so people don't want to be seeing multiple Threeven petitions, but you can do your own work in the world. You can start spreading the term around society. You can start just using it in day-to-day life here and there. You're like, okay, we're going to buy a pack of eggs. All these packs have a Threeven amount. Or you could be like, okay, so there's 6 of us at this party. Good thing there's a Threeven amount of donuts. So if we wanted, we could all have the same amount, And there even would matter there too. A reminder that Threeven is not trying to steal the credit from even. Threeven is simply trying to share it. So, okay. That was a little comment one right now. And feel free to leave more comments if you'd like, because I will be checking them here and there. But as you know, I get wrapped up in the things like the graphs and then skip the comments for half an hour or so. But I do look at them here to there. So luckily we can do fractions. That's pretty cool, because now we can just test what some basic fractions look like. And first, to do that, I actually want to go back to one of our simpler ones. Let's go to the double cosine. And let's make it a little bigger. Let's make it 20 pi. It goes to. Now, here we're at 13 thirds, but let's start looking at some simpler fractions. We're going to be looking at the fractions. This is related to what's called a fairy series. We're going to be looking at the fractions basically with numerators and denominators up to a certain point. We're not doing exactly a fairy series, but don't worry, that will show up in my Euler's totient function episode when that comes, because they're related. And let's start with looking at all the ones that are going to have a numerator or denominator up through 5. So we'll begin with 1/5. And we're going to begin by going through the fifths. So the fifths are doing kind of strange things. Here we hit 1, that's fun that at this range, that's what 1 looks like. Now, let's go to fourths now. There's 1/4. 3/4 would be like that, which is 3-like and almost forms this like, that shape in the middle reminds me of this shape that rolls really well. I'm forgetting the guy's name, but it's called the something triangle. It's not the Sierpinski triangle. It's not Pascal's triangle. There's a lot of good triangles in math. There's another one that some guy, some guy's name in the triangle. It has a special quality about how it rolls. You could, like, for example, put it between two flat things and it would slide perfectly despite looking triangular. It is a shape of constant width, as you'd call one of those. If you're curious what I mean, I do forget the guy's name, but look up shapes of constant width triangle and you'll find it. Now, A being 4/4, of course, sends us to the same thing that 5/5 did. But 2/4 will send us to whatever 1/2 does, and it gives us that skewed circle. Now let's try the thirds. And actually, let's try 5/4, because we might as well try, well, not 54, 5/4. And this is very 5-like, but it's kind of like the 4 is screwing with it. So now let's do thirds. And, well, let's do more of, if we're going to let numerators be larger than denominators, we should probably do the ones that would be something over 1, which are these. I guess I should make it so you guys can see the number that I'm talking about. I'm not sure if you can see that. Let's put me a little bit to the side so you can see what number I'm doing. Now, that's 4, and as we see, they double when they're a single whole number. These are the equivalent of that over 1 in the game we're doing. Now let's see the ones that are over 2 where the numerator is larger. 3/2, 4/2, and 5/2. Now thirds, finally. This is 5/3. That one certainly is the most chaotic looking one yet. You have 4/3. And, 3/3 is going to look like the good old 1. 2/3. And you got 1/3. Now remember, it really depends on the range that we're doing. So just as an example, let's look at all the sixths under some different ranges. So, and the way I'm going to do that quicker is going to be, when it's fractions, am I still allowed to set the thing? So I want A to equal something, and I want to see what the step is, but then I want to turn it to fractions. The step's going to be 1, and I'm going to be ranging from 1 to 6. Well, if we're doing sixths, let's say we're ranging from 1 to 12. And the step's going to be 1. That means that it's going 1 at a time. So that I can just click up the bar and it'll go 1, 2, 3. Now, let's see if I can still make it fractions and do that. I'm not sure. No, I don't get the bar anymore. Okay, I like Desmos. There could be a workaround, but there are things about it that frustrate me too, like that. It's like I get to either do fractions properly or get the bar. Oh, is that just because I was just, like, define it? Let's see. So, from there, if I make that, I clicked below and got the bar. So maybe if I make it, click below, and then turn it into a fraction. No, I don't get the bar. I have to pick one or the other? Okay. We're going to pick this. I'll just change the numbers. So that was an example of when we were looking between 0 and 20 pi. Let's look at a symmetrical one. Let's do negative 12 pi to 12 pi. It started at 0 to 12 pi as the default. So A is 1/6 here, and I'm just going to have to manually change them if I want the fractions correct. 2, 3, and these are round of sixths. 4, 5, 6, 7, 8, 9, 10, 11, 12. Now, here let's try a less symmetrical one, but ranging smaller or lower amounts. So what we'll start with is going, what if we just did 6 pi and just saw smaller versions of the shapes? We're going to zoom in a bit for that. And you know, we're going to try something funny. We're going to flip the inequality. Uh-oh, it just went to 6. I accidentally missed the sixths. All right. Now, what if we went to a much larger number, like 100 pi? This is when we had the inequality flipped. Let's reflip it for now. Uh-oh. For some reason, when we reflip it, I can't see anything on 12 sixths. Can I see anything on any of the others? Not at this scale. All right, well, let's flip the inequality back. Look, good thing we tried that. So, 1/6, 2/6, 3, 4. Let's see what this looks like further away as well. 1, 2, 3, 4. So those are pretty fun to mess around with and see all the weird things they cause. When we put the range too high, it blots out too much. So we're going back to how it was, which is that the shape is the main one we're seeing, and that we're only going to 12 pi, but we're going to have a few at once. So now we're going to just go here, and we're going to have a slider for A. And we're going to see what happens when we loop around with two different ones. One is the double sine, and one is the double cosine. That's fun. What if we put one of them to be the reverse inequality? Oh, that was equal. And one to be the inequality. Now, it also looks a little different depending what you have on top, because they make one brighter than the other. That's pretty neat, although the background isn't really changing. Let's say the one that has the flipped inequality gets a larger range. Okay, that's pretty neat. Let's see if we're able to animate it slow enough that it doesn't look like chaos. It is, but it's not getting them all. Or no, it is, because I'm doing 0.1. I guess, will it do 0.01 for my step and do it efficiently enough? Yeah, there we go. That is wacky. Whoa. So, where do we go from here? The first obvious thing I think is we just have to try the opposite, where we flip which one got the bigger or smaller inequality, and we also trade that it got 50 pi and it got 12 pi. Now, I'm thinking that 50 pi was a little too much for this. It might be the scale, but well, why does 30 pi seem worse? Okay, 20 pi. It's getting darker and darker the less I tell it to look at. That's weird. Maybe we want that one in front, to be clear. Yeah, that blots out too much this way. I guess it's just the color. Let's make the color lighter. It's still just blotting out so much. So we're going to go back to our 12 pies. Somebody says you can even set the range to other variables you like. Cool, let's try 12e. We are now going up to 12e instead of 12 pi. It's funny because I've tried to set more than 4 variables at once. So it starts with A, B, C, and D. But if you try and set a variable as E, you get really confused because you're like, why is it a constant? Why is it not a variable? And it's because E is an important enough number mathematically that they don't have it built in as a variable. They have it built in as the number. Okay, yeah, we got the name of the triangle I was talking about earlier, the rouleau triangle. Or I'm probably pronouncing that wrong, but something like a rouleau. Now, somebody says, how do they get good at arithmetic? They want to ditch their calculators. Good question. I would say it takes a lot of doing it in your head. And when I release the full notes of my Numberations card game that I've been still working on, that will actually help with all the 2-digit arithmetic, remembering like, is this number 3 even? And what do I get if I divide it by 3? Things like that for 2-digit numbers. It will help. In general, I would say you need to learn like little hacks. For example, if I'm multiplying 13 by something, maybe I see what is 10 of it plus 3 of it. If I'm multiplying 19 by something, maybe I say what's 2 of it, add a 0, minus 1 of it. And there are tricks, and I haven't really made an episode about that yet because I prefer to make a lot of my content about things that I didn't know before in life. Like I didn't learn them in school or I didn't learn them as a kid. And then when I found them out, it was like, whoa, more people should know this. And pretty much everyone learns in school, like, here's a few arithmetic tricks. They don't necessarily learn the best ones, but it's not as rare or new of a concept to be like, quick ways to multiply numbers. And I have fun making rarer, newer concepts. Or, so, like, I would say on the Combo Class channel, a third or half of the episodes are, like, my take on a classic mathematical thing. But at least half of them are something that I'm just like, this is new. I've never seen this before. I can't believe I learned this or figured it out. And so there will be a time when I make an episode or bonus videos on this channel about more hacks of how to quickly multiply things and such. However, I will also say there's nothing really wrong about trusting a calculator. Being a mathematician does not mean you're good at arithmetic. Those are almost separate things. Being a mathematician means you know what it means to get a result to a problem, how to seek out a result to a problem. It means you've studied various fields and their connections. It does not mean it's more creative and less methodical as some people think. It is methodical in terms of you do need to study the past history of what has been learned so far, but you don't necessarily need to study what's 67 times 34 off the top of your head. Now, you do want to know tricks, like just simple rules. Like when you multiply two numbers, the only thing that'll affect the new last digit are the old last digits. You want to learn like simple tricks, and I will at some point make an episode full of those. There have been occasional ones scattered through my shorts. Somebody asked what I do for a living. I had been a music teacher for a while, and then you got to watch the Grade -1 documentary if you want to see the details. But basically, I had to get multiple surgeries, had a really hard year, and after multiple surgeries, I kind of had to stop quitting, or I had to quit music teaching for a while. And then we started to get a bunch of subscribers on these channels that are only about 1.5 years old. So I'm hoping this will be my future job. Somebody said they got here from the Combo Class Discord server. That is a cool server. I don't check it nearly enough, but I do almost always alert people when I'm about to start a stream on there. So, and sometimes I chat about random stuff there. So, lots of fun comments, and looking at where we go from here, well, to merge it with those backgrounds we made earlier, What we're going to try is we're going to see how... Uh-oh. Okay. The background music went to my audio mix of one of my episodes. Okay, we have to go to the next actual song. Okay, we'll pause the background music for now because I'm thinking before too long, what we're going to do is take our field trip to the classroom now that it's been an hour, where we are going to see the chaos that is ensued. So as soon as I start heading outside, to anybody who prefers to see the chaos ensue, or wait to see what sort of chaos ensues for the episode, wait. At some point within a week, I should hopefully have the next episode out. It's not done filming, so it'll probably take up to a week to be ready. The next episode is going to relate to my... This is in the category of not like new and unique as much as my different type of presentation of a classic thing. And the classic thing is the different types of infinity, nicknamed uncountable and countable, the cardinal and ordinal numbers, Cantor's diagonalization theorem, and in short, the like hook or synopsis of the episode is, out of things like the natural numbers, fractions, and real numbers, which of these are different infinities and why? So, which again is a kind of classic math concept, but I do have a unique take on certain parts of it. Now, we are going to take a brief field trip in a minute to see the chaos that has ensued. And like I mentioned, similar chaos ensued partially through grade -1, and it turns out it was time to ensue in grade -2. So the last things we'll try on our graphs first are going to be seeing, what if we put this over a mod function? We can either put something like mod x to a variable like a, or we can put something like mod... Well, are they going to let me do mod x, y? Yeah. Now, no, they're not. Too many variables. I don't know what to do with this. Are they going to let me do mod x1? They don't like mixing polar coordinates with mod stuff, unfortunately. So we have to do something like y if we want to see that happen. And we have to turn the thetas back to either x's or y's. But that's what that one looks like. If I make that, it looks like these interesting spiky hills. And if I had said mod x, y instead, we would get that. If I had instead not had an a, we'd get that. If I had replaced one with sine, we'd get similar. And, oh, double sine does change it. And we will next see cosecant. There's cosecant on 1. Here's cosecant on that one, similar. Here's cosecant on both, similar. Even if I replace 1 with a cosine, it's a little bit different. If I replace one with the tan, it does often get different. Both tan, it's surprisingly similar, but I think that could be the scale we're at. So let's zoom in and see why they're looking so similar. So like they're up close, we can see some more of the differences. There's, if we have a tan then a sine, this is double sine. This is sine cosecant. Here's like if I change the mod to a constant instead of, see, e they treat like a constant. If I change it to y. And what if we switch it? What if we have this over this? Uh-oh. This is getting crazy. There. No, that's not what I wanted. There. No, that's not... what I wanted. When did it? Okay, how do I get this? Okay, we're just gonna make a new one. That over this. So that's what this one looks like. The one I was trying to make. It's pretty neat. And we could try replacing some of these with Y or A. There's Y, there's A. What about this one? There's a Y, there's an A. What about some of these? A. That one looks interesting. Whoa. Here's if we go, what if we're just like 1 to A? Or what if we're like A to X? Each of these has their own unique, strange differences. Whoa, as we go and we do enter one of those infinite corridors. Any of y'all ever read House of Leaves? This reminds me of that. Okay, great book, by the way. Very, very weird book, but great. Lots of fun chatting here, and it is about time to take a brief field trip before we wrap up our stream. So, for our brief field trip, while I transfer us outside, I am going to have you guys just look at an animation. So, let's go back to one of our fun animations. Was this one of them? No, this one had a problem with it. This one, maybe the problem was just that I'm either too close or too far. I think I'm too close. Yeah, I'm trying to zoom out, but I'm still really close. I'm zooming out as fast as I can, folks. Okay. Now I'm starting to see more detail. There we go. Now I'm actually seeing 2 colors. This one is still very spiky. Perhaps it's the range it was at. Yeah, it's the range it was at, essentially. This one is pretty wild. I like to look at that one. That one's cool. Now, let's see how the animation... No, the animation of that is far too fast. But maybe I can fix that by making the steps slower. No, that did not fix it. So, that's because we had cosecants. Cosines looked cool. What if we have one of each? Still way too fast. These are some of the ones that start to look like bugs when you're at the right point. Tell me that does not look like some type of bee or fly. Some of them look even more like a bug. That was a previous one we did like this, was finding bugs in polar coordinates. Now, we also find a lot of flowers. Now, see, even negative 2.5 for A has a 5-like thing and a 10-like thing in their own ways. And we could argue a 2-like thing, which is not because it's closer to 2, it's because 2 is the amount we'd need to multiply this to hit an integer based on, the back and forth, or the percentage of each. Now, when we put them both to cosine, we had a lot more luck watching the animation without it being like too hyper crazy, but we also had it set a bit lower, I think, and I think we're a little closer. So here we go. And let's try a little higher. Let's try like 15 pi. There we go. So this one's slightly newer. And it was kind of fun when we had 2 going at once. So what I'm going to do is I'm going to copy this with the mildest variation. Here's what we're going to do. Instead of A theta, we're going to make this one 2A theta. I guess I didn't need the parentheses. I was thinking of doing like A plus 1 theta or something, but I think this would line up more easy and often. And we are going to make them different colors to see when they line up. This one was a little big. We'll put it back to 12. So now they're even. Okay. Which one should be in front? I think the red in front. Now, whoa, and it slowed down. Now, it hits amounts that get pretty high. When we get up to 10, there's going to be like 20 spikes. So I don't think we need to go negative 10 to 10. I think we're going to go from 0 to just 6. Because that's like the maximum amount of spines we will see right now, which is technically should be like 12 spines in certain ways, but there's a lot of different layers of spine. It's kind of interesting how when these parts hit the axis, they vanish. Do you see that? But that is likely based on the 12 pi caliber. Oh, you know what's funny? You know, I said 12 pi is probably slightly under 40 because I quickly did the math in my head. Guess where they're hitting? Slightly under 40. So they must be hitting at 12 pi. If I had raised these to 15 pi each, they would be passing and vanishing at a different point. In fact, you know, to watch a newish type of thing, we're going to set these down to 6 pi and we're going to go up close. And it might look more boring in a certain way. So what we're going to do to fix that is we're going to make the green one go the other way. And now we get our kind of cool weird shape for a moment. I'll put one of my beats back on again. And then we will move outside while I do this. Let's see. All right, folks. We're here in the combo classroom, and it's time to say goodbye to today's wacky shapes. But don't worry, I like doing this. Every, 5th or 10th stream will involve some wacky graphs. And now that we're in the combo classroom is people's chance if they would like to wait to see a particular bit of chaos until the next episode drops, which should be, I don't know, about 5 days from now or something. Should be a week or less from now, hopefully. The bit of chaos that I alluded to that occurred in grade -1 and has reoccurred, and I knew it was going to occur because a certain important part of the classroom gets rained upon a lot, and the rain and has a lot of things stacked on it, and the rain and the weight sometimes cause the legs to shift a bit, and the legs had gotten to the shifted enough point that I knew that one of these times that I leaned on my desk, it was going to go diagonal again. I'm not sure. Can you even see what's going on here? Here's a 5x5 Rubik's Cube. You can barely even see what's going on here. I should have brought a candle. this is the desk. It is diagonal. And there was a whole arc of grade -1 where the desk was diagonal that was quite silly and fun. And we are at that arc again in the final quarter of grade -2. Sometimes things collapse near the end of the grade. And remember, for one, I have two philosophies about this. For one, you must have destruction to have room for growth. For two, you must, or the 2-1's not a must, but the 2-1 is, it is better to destroy something in a documented way where it gets to live and then is documented for history to teach and learn from than to let it collect dust on a shelf. I don't think this desk would fit on a shelf necessarily, depending what type of shelf you got, but in any case, we are at the crooked desk time of the season. Things are also still quite collapsed more than ever back here. I don't know what degree of this you can see, but there's a lot of chaos. Anyways, thank you for joining me today in combo class. I mean, we're only in the combo class for the last second, but thank you for joining me for a Demotro combo stream. And we'll show our graph for one last time. I will catch you all again before long. I love all of you. Remember to watch the new combo class episode linked in the description. Modular exponentiation if you haven't seen it yet. Remember, if you like this type of stream, to go through the live tab on this channel and look for the ones that look similar, because we do stuff like this every once in a while. And also remember, if you want, look for other links like the Discord or Patreon or subreddit or stuff. You are all my combo lords. You are all the best, and I will see you again very soon.